Hey everyone, so hopefully you already printed out the notes, the blank note copy from Blackboard. If you haven't done so yet, then please do that before you watch the video. And then fill in the notes as we're going along and bring those notes to class so that I know that you watched the video and do the homework that I assigned, the problems I assigned are on Blackboard. Also in the email that I sent to you. Anyways, so we're doing exponential growth and decay, and these are just applications of what we've been doing already. So you pretty much know everything that we're going to go over. It's just how to apply it now. So, exponential growth and decay. If you see this statement, the rate of change of some quantity p is directly proportional to p, you're going to write the following, because directly proportional, if you remember from Algebra 2 or pre-calc, whenever you say directly proportional, that's, if you remember the function y equals kx, well, if it's directly proportional, the rate of change of some quantity p is directly proportional to a value p. Well, normally it's y equals kx, but if it's the rate of change, then we're going to write dp dt for the rate of change, and then p is just p, right? So the formula then becomes dp dt equals kp, which is a differential equation. So if we want to solve that differential equation, we would have to separate and integrate dp dt equals kp. So we get all the p's on one side and all the t's on the other. So I put 1 over p, I divided p onto the left side, and I multiplied by dt onto the right side. And now I'm going to separate, I separated, and now I need to integrate it. So when we integrate it, we get ln, absolute value of p, equals kt plus c. And then how do we get rid of the ln? We get rid of the ln by exponentiating both sides. So we exponentiate both sides. And then we get p equals, and we'll move that constant that's in the exponent to the front of the exponential. So a e to the kt. Alright, so anytime you see the rate of change is directly proportional to p, the differential equation is dp dt equals kp, and the original function is p equals a e to the kt. A is your initial condition. So it's your whatever your starting value is. That's what A will be. So anytime you see directly proportional, remember that dp dt equals kp and p equals a e to the kt. You might remember p equals a e to the kt when you guys were doing compound interest in Algebra 2. Do you remember p e to the rt formula from back then? It's the same thing because the rate is directly proportional to the value that you have in the bank at that time. So that's why compound interest uses that formula as well. Anyways, example 1. You run over a nail as the air leaks out of your tire. The rate of change of the air pressure inside the tire is directly proportional to that pressure. Write a differential equation that states the fact that if the pressure is 35 pounds per psi and decreasing at the rate of 0.28 pounds per psi per minute at the time the nail is struck. So our two formulas, dp dt equals kp, because it's directly proportional. I'm going to use 0.28 for dp dt because that's the rate. My pressure is 35, so solving for that variable k, I'll plug in 0.28 for dp dt, I'll plug in 35 for p, and get 0.008 for the value of k. So, my differential equation is dp dt equals 0.008 p. Now if you notice really quickly, I wrote negatives for the 0.28 and then my K I replaced with a negative 0.008, and that's because the pressure is decreasing, so I wanted to make the rate a decreasing rate, so I made it negative. So just make sure you put little negatives in front of your 28, 0.28 and 0.008. Okay, solving the differential equation. P equals AE to the KT. A is the initial condition. We started off with 35 pounds per PSI. That was our pressure. Our K was 0.008. Oops, sorry. Let me go back a second. Our K was negative 0.008 T, and that's our differential equation. All right. So, what will the pressure be 10 minutes after the tire was punctured? Use the equation that we just found, P equals 35E to the negative 0.008 T. Plug in 10 for T, and you should be able to solve the equation. I just plugged that value into my calculator and got 32.309 pounds per PSI. Okay, and then the car is safe to drive as long as the pressure is 12 pounds per PSI or greater. For how long after the puncture will the car be safe to drive? So I plugged in 12 for the ending pressure amount. 35 is still my initial, negative 0.008 is my K, and we're solving for T. So divide by 35, and then we're going to ln both sides to get rid of the E, and divide by negative 0.008, and so T equals 133.805 pounds per PSI per minute. So that is example 1. All right, for the next example, the example 2 and example 3 on the back, I would like you to try those on your own. So pause this video, try those 2 problems on your own, and then right after, unpause the video and you can check your answers, and I'll go over how I did them. So pause now, do the problems, and come back to me. See ya. Okay, hopefully you did the example 2 and example 3. I have my answers up right now. My differential equation is the same as it was for the problem before. dP/dt equals Kp. P in this case is price. And then my value of the car is P equals AE to the KT, just like normal. Suppose you own a car whose trade-in value is presently $4,200. 3 months ago, its trade-in value was $4,700. Find the particular equation that expressed the trade-in value since the car was worth $4,700. Well, if we want to know since what it's worth since it started at $4,700, then $4,700 is our initial value. So I plugged in $4,700 for A. I plugged in $4,200 for our ending amount, and I plugged in 3 for 3 months ago, and then I can solve for K. So divide by 4,700, take the natural log of both sides, divide by 3, K is negative 0.037. So my equation would be P equals 4,700 e to the negative 0.3037 t. What will be the trade-in value of the car 1 year after the car was worth $4,700? That's $2,997.12. You plan on getting rid of the car when its trade-in value drops to $1,200. When will this be? At 36.414 months. At the time your car was worth $4,700, it was 31 months old. What was its trade-in value when it was new? So I plugged in negative 31 for time, since at 0 it's 4,700. Then if I wanted to know 30 months before 4,700, it would be a negative 31 because we're going back in time. You could also solve it the other way by redoing the formula and putting 4700 as your P and 31 as your T and solving for the A value. That's fine too, but I think this works just as well. Okay, and on to example F in the next example. Okay, I said that the difference could be the mileage on the car. You could say car accidents or nicks on the car, or paint job, or whatever you want to say for F is fine. And then most of you have done half-lives already in chemistry, so I won't go over this too much, but I'm going to use the formula P equals AE to the KT. If 10 grams were present originally, then if its half-life is 5,730, then half of 10 is 5, and then time is 5,730, and I solved for the K value. K comes out to be, in your calculator, negative 1.209 e to the negative 4, so you can translate that to negative 0.000129. Create an equation, 10e to the negative 0.0001209 times 2000, and you get P equals 7.185 or 815 grams. So that's how you do example 3. On to logistic growth. So most of the things for exponential growth and decay, they continue to increase as you go towards infinity, or they continue to decrease as you go towards infinity. But when you think about it, most of the things in life have a limit to how much it can increase, right? So if you think about purchasing and or the rate at which people purchase the new iPhone that comes out. So in the beginning, everybody buys the new iPhone, right? And then it continues to increase until at some point it levels out and people aren't buying the new iPhone anymore. Well, what it's called when it increases and increases and then it levels out is it's called a logistic growth function. So that's the next thing that we're going to be doing. All right. So logistic growth. If you look at the graph, the blue graph that I drew up there, that's a logistic growth function. It grows exponentially, and then at some point it levels off at the top. So that's called, it reaches a limit up there. So the red dotted line is the limit at which the logistic growth levels off at. So, like I said before, in exponential growth, we assume that the rate of increase or decrease of a population at any time t is directly proportional to the population. However, in many situations, population growth levels off and approaches a limiting number, the carrying capacity, because of limited resources. In this situation, the rate of increase or decrease is directly proportional to both p and L minus p. L is the limiting number. This type of growth is called logistic growth. It is modeled by the differential equation dp dt equals kp times L minus p. We're not going to solve for p of t right now, so we're not going to separate and integrate now. We have to learn partial fraction decomposition, so we'll come back and do more logistics when we get there. But if we find d squared p over dt squared, the second derivative, we can find out an important fact about the time when p is growing the fastest. So that's that dot on the graph that I drew up there at the top. That is the inflection point of the function. So that's when it changes from increasing to decrease, or concave up to concave down. Remind me to tell you an interesting story about that point in class on Thursday or Wednesday, because it's kind of cool what some businessmen are using that point for. So anyways, let's do a problem. The population P of T of a fish in a lake satisfies the logistic differential equation. dp dt equals 3p minus p squared over 6,000. Now that doesn't really look like the function above. However, it just doesn't have a p factored out. Anyways, if you want to find the limit as t goes to infinity of p of t, well, the limit will be where the first derivative equals 0, right? Because it's got to reach a horizontal tangent line. That's where your limiting factor will be. So if we set dp dt equal to 0, first I'm going to factor out a p. See, a 3 minus p over 6,000. Set both of those equal to 0. So p equals 0 and p equals 18,000. The limit as t goes to infinity will be 18,000. And the range, since p of 0 is 4,000, the range starts from 4,000 and goes to 18,000. Okay, for what values of p is the solution curve increasing? Well, I already found my critical values of the first derivative, so let's plot 0 and 18,000 on the first derivative. Don't forget to label your number line. 0, 18,000. And it's negative, positive, negative. Plug it into the first derivative equation. So, remember, the range of my solution curve only goes from 4,000 to 18,000. So I don't need anything less than 0. I don't need anything greater than 18,000. So I'm only increasing on the interval 4,000 to 8,000. Restrict it to the range of your solution curve. Okay? For what values of p is the solution curve concave up? Well, we have to find the second derivative. So first, let's find the second derivative. 3 dp dt minus 2 over 6,000 p dp dt. I'm going to factor out a dp dt because that's what they both have in common. So 3 minus p over 3,000 times dp dt. I'll do a number line for that. Don't forget to set both of those equal to 0. So p equals 0, 9,000 and 18,000. The 9,000 comes from that inside parentheses, setting that equal to 0. The 0 and the 18,000 come from where the dp dt equals 0. So that was from the previous problem. So graph those three values on the number line for the second derivative. Don't forget to label your number line. If I plug in on the left side, I'm going to get a positive, and then the first derivative is negative. So positive times a negative is a negative. Between 0 and 9,000, the inside of the parentheses comes out to be a positive value. dp dt on the interval 0 to 9,000 is positive, so that value is positive. From 9,000 to 18,000, 3 minus p over 3,000 is negative. 9,000 to 18,000, the first derivative is positive, and so that's a negative value. And then greater than 18,000, 3 minus p over 3,000 is positive, and dp dt is negative, so that's a negative value. But remember, I'm only looking for the interval 4,000, on the interval 4,000 to 18,000, so I'm concave up on the from 4,000 to 9,000, and then I'm concave down from 9,000 to 18,000. Does a solution curve have an inflection point? Justify your answer. Yes, it does, at p equals 9,000. And I didn't justify there, but you would want to say the second derivative changes from concave up to concave down. Or no, you would say the second derivative changes from positive to negative at 9,000. Alright, use the information you found to sketch the graph of p of t. Well, we know there's a limit at 18,000. We know our initial value is 0, 4,000. It increases constantly, but it's concave up and then it's concave down, and the point of inflection is 9,000. So, sorry. Okay, so that's that. Then example 2 and example 3 are pretty much the same, only they have a different initial condition. So that changes your answers to a lot of these problems. So I'm just going to put up the answers to 2 and 3, and you can check your work. I would like you to try them on your own first before you take a look at the answers. So try them on your own, then check your answers with the ones that I posted. Pause it so that you can look at the page for as long as you need, and then we'll go on from there. Okay, here's example 2. The limit is 18,000. The range is from 10,000 to 18,000. I took the number line from the example 1, so it's increasing from 10,000 to 18,000. I took the number line from example 1 again, and it's concave up from 10,000 to 18,000. This time, there is no inflection point because the inflection point is not included on the range of the solution curve. So since 9,000 is not in the range, we're not going to include it as an inflection point. That means that it's just always concave. Sorry, this should say concave down. And less than 0. So it's always concave down from 10,000 to 18,000. And that's about it for that one. Then example 3, it starts at 20,000. So it starts above the limiting capacity. So let's show you the answers to number 3. Okay, here are the answers to number 3. Your limiting value is still 18,000. Your range is from 18,000 to 20,000 this time. Decreasing from 18,000 to 20,000. It's concave down from 18,000 to 20,000. There is no inflection point on this solution curve, and the sketch starts at 20,000, decreases to 18,000. It's always concave down. Alright, so now your homework for tonight is for you to do the worksheet on Blackboard, do 3 problems on page 1, and then do 4 problems total on page 2 and 3. So page 1 is exponential growth and decay, and page 2 and 3 are logistic growth. So I would like you to at least try 3 problems from exponential growth and decay, and then do 4 problems on logistics. However, if you want to do more, you can do more. All the answers are at the bottom of the page, so feel free to look at all the answers and check your answers as you're going along. And remember to bring this note sheet that you completed, as well as the homeworks to the next class that I see you, so that I can give you a completion grade on it, so that I know that you watched the video A and that you understand it and did some of the homework. And then come to class with questions if you have them, and I'll answer anything that you might have. And that's about it. Alright, I'll see you guys soon. Bye.